All right, well, go ahead and get started here. And as people come in, we can keep going. So here's our haiku for the day. I don't know, it seems blurry to me. Does it seem blurry to y'all today? The haiku says, skilled in statistics, mathematical masterminds learn from Simpson math. Let's see if it actually fits the pattern. Skilled in statistics, mathematical masterminds learn from Simpson math. Hey, it actually does fit the pattern. 575, that haiku there. Our morning haiku. Here's our early bird. Researchers gather measurements. Measurements. Is there an E in there? From athletes and spectators at a 5K run and organize the information into a two-way table. So maybe you remember in the past, we've made two-way tables before. Back when we did graphical displays, we did two-way tables. Hey, Bo. So we've made these before. Today we're just going to create them again, but with some, and they're going to be a little bit harder because we're going to use those words of sensitivity, specificity, and prevalence. So remember, with a two-way table, we're really looking at two qualitative variables. So in this case, I'm asking who's showing up at the 5K? Who's there? We missed the 5K this last weekend. We were supposed to get to go to a 5K and run in the 5K, but it was canceled. Darn. So if we had gone to the 5K, we would have looked to see, and some of them would have been athletes, you know, the people walking and running, and some of them would have been the spectators just standing around watching. And then we've got a actually the total of those is down here at the bottom. And then as they were running, or after they were running, or before they ran, probably before they ran, they took their blood pressure to see, and they categorized them as either high blood pressure or normal blood pressure, and then their totals. And so here we've got it already started, and we can fill in the rest of it. I bet you can fill in the rest of it. So I don't know, where do you want to start? If we have this is the total number of people that came, were 30 people total. And we know that 20 of those people were spectators. So just 20 of them were wandering around. Good, Amani. So we know this one's going to be 10, because 30 minus the 20 gives me the 10. So there were 10 athletes there. Great. What else do we know? We can fill in some other stuff. From that, maybe we know that, well, since there were 10 people with normal blood pressure, that tells me that there are, since these have to add up also, then I know that, oh good, that too. I know that this one has to be a 20 high blood pressure. And you're right, since there were 2 athletes with high blood pressure and a total of 10 athletes, there have to be 8 of those athletes with normal blood pressure. And then we just do some addition and subtraction, right? So we say, well, 20 minus that 2 means that 18 of our spectators had high blood pressure. And 10 minus the 8 means that 2 of them had normal blood pressure. Perfect, perfect. Okay, so, and then we can check ourselves by just adding them up that direction, and our rows should add up. Then we can look and start to, look at the data to say, well, our 18 spectators had high blood pressure, or 8 athletes had normal blood pressure. So maybe you kind of remember how to read those two-way tables. And maybe we even did some probability questions with them. I don't know, did we? Like, what if I ask you, what is the probability? What is the probability that if I randomly select somebody, I'm just going to randomly select somebody at that 5K, what's the probability I get someone with high blood pressure? So I'm just going to what is the probability If randomly select a person that's there. I'm going to randomly select the person that's there. Then what's the probability that I get somebody with high blood pressure? Good. High blood pressure is a total of 20 people out of the 30. Great. So 20 out of 30, which equals, you're right, 2/3 of my people there have high blood pressure. Then, what about if I switch it up just a little bit? What if I say, what's the probability I get, instead of a person, now I'm going to randomly select a spectator. So now I'm only looking at those spectators. What's the probability I get someone with high blood pressure? So this is when I'm looking at everyone. But what about if I'm just looking at my spectators? I'm only randomly grabbing from those spectators. What's the probability that I get someone with high blood pressure? So in that case, I'm only looking at these 20, right? I'm only looking at the 20 spectators. And of those 20, there are 18 spectators with high blood pressure. So divide by 2 and you get 9/10. So 9/10 of them, oh yeah, I like the 18 out of 20, yeah. 9/10 of them, of the spectators then have high blood pressure. Good job. Okay, so we've done a little bit of this maybe in the past. By the way, we call that conditional. Do you remember calling that conditional probability? Where it was on a condition, we knew that there were a spectator. So then it changes my denominator because I'm only looking at the spectators. Tomorrow, that's really what we're going to be doing, is just looking more at conditional probability. But we're going to use something called Bayes' theorem to help us out. Okay. So today, though, we're just going to work on making two-way tables. And you learned yesterday with your pre-learning assignment, we stole an activity from, I think it was Nottingham University, to teach you about the words sensitivity. So tell me, what does this word sensitivity mean? What does it mean, sensitivity? If I'm talking about a diagnostic test and I ask you what's the sensitivity of that test, what does it mean? Perfect. So that's exactly it. It's the test's ability to show when I'm sick, if I go in and have a test done, what's the test's ability to actually show a positive test? So, you know, especially in this time of viruses, but this is true all of the time where you go in and you have a test done. So for me, usually when I do this lesson, I teach about when I had my mammogram. So I'm to that age where I now have to go in and have a mammogram. I'm old enough now. And so I went in and had a mammogram done. And when I went in to see the mammogram, the reason they have us go in to do that is because it could show breast cancer. And this sensitivity is what's the probability or what's the percentage of those people who have breast cancer that it actually catches. So a true positive, what percent of the people who actually have the disease does it say, yes, you have the disease? Good, y'all did a good job of that. So the sensitivity is the test's ability to say positive or to come back with a positive result when a patient has the disease. Mr. Simpson can probably do better with the wording. He's got better words than me. So, or you can think of this as the true positive. You have the disease, and it tells you you have the disease. So when I went in for my mammogram, like a week later, I ended up with a letter in the mail that said that I was positive, that the mammogram showed something. So I got that positive result back. So here's the question is, was that a true positive? And at what rate does it actually show that you have breast cancer? So, or like when you go in for a swab on your throat for strep, and they swab you, or nowadays for coronavirus, when they swab you, what is the percent of people that actually have the disease that walk away with a positive test? So that's what a true positive is. That's what that sensitivity is. Okay, what about specificity? What did it mean, specificity? What was that word, specificity? Yeah, it's the false or the true negative. Yeah, it's the same thing, but for negative. So in other words, if I go in and I don't have breast cancer, then what percentage of the time will it tell me I don't have breast cancer? Or if I go in for a swab and I don't have strep throat, what percent of the time will it tell me that I don't have the disease? And or coronavirus or whatever. So this is the testability, or the percent of the time to say negative when we don't have it. So you can think of that as exactly right, the true negative. This is your true negative. They don't have it, and it truly says they don't have it. True negative. So this is your true positive, this is your true negative. And it is kind of hard to remember which is which. I always remember because the letters for me are backwards. Like this should be negative because it has an N, but instead it's positive. And this one's P for it, which is backwards. It should be it should be an N in there. So it's like they're backwards for me. That's how I remember. But other people have other ways of remembering it. You know, like you're sensitive to diseases when you're positive. You know, you're sensitive when you're sick. So that gives you sensitivity. I don't know. Come up with some way to help you remember which is which. Then, what about, did it also have this word prevalence? Now I can't remember if it did or not. The prevalence is how often does it show up in the population? Or how much of the population has the disease? So, how much of population has the disease? So these words are going to be really important. Oh, it did at the beginning. Okay. How much does it show up in the population? So if I say that 1%, yeah, Bo, that's exactly right. The commonality of it. So like if I say 1% of the population has 1% of women my age have breast cancer, then 1%. Is if 1% of women, well, that means 1 out of every 100 women. You know, if I gathered together randomly a group of 100 women my age, I would expect one of them to have the disease. That's what that prevalence means. So the prevalence tells me out of the population. Now, what would happen though if I gathered together 1,000 people? So if I gathered together 1,000 women, well, if I expect 1 out of 100, then out of 1,000, I would expect 10 people to have the disease. Because I multiplied my denominator by 10, So I multiply my numerator by 10. What if I had 10,000 people? Now how many people would have the disease? Yeah, that's exactly right. You're just multiplying that bottom by 10. So we multiply our top times 10. So we end up with 100 women out of 10,000 people would have the disease. Now, we know how to do this, how to make equivalent fractions. This is going to be important as we make our two-way tables, just because it's going to make our math a little bit easier for us as we go through. And it's good to know that, 1 out of 100 people means if I've got a population of 10,000, maybe my city has 10,000 in it, well then I would expect 100 people to have it. So as you start thinking about like the coronavirus and what percent of the population has it, say 40% of the population get the disease, well you go, well that's 40 out of every 100. If Temple is got 100,000 people in it, then how many people would actually have the disease? So when you start hearing that prevalence, you can start comparing it with different sizes of populations. Okay, so these three words are going to be super important today. Prevalence, how much of the population has the disease. Specificity, when the test says negative and the patient does not have the disease, what's that percentage of the time? And then the sensitivity. So hopefully you looked at all those yesterday, got a warm-up of those words, and then we're going to use them today. All right, let's practice making some two-way tables. And then tomorrow, we're going to use the two-way tables to help us to find the probability of different things, just like we did with the spectators and the athletes. So the first step, though, is going to be being able to make those two-way tables. So we're going to practice that today. Okay, so here we've got the crime scene reenactment show that a particular witness has a 75% chance of identifying a perpetrator's race, white or black, correctly. The population of potential suspects is 84% white and 16% black. What we are going to do is we're going to create a two-way table. And then tomorrow we're going to look at finding probabilities of things. But today we just want to put this information that we have on a two-way table. So the first thing we're going to do is we're going to look for our two variables. So remember, a two-way table, we've got two different qualitative variables that we're looking at. So do you see one of the variables on there? What's one of the variables I'm going to be representing with this particular scenario? Crime scene reenactment show that a particular witness has a 75% chance of identifying a perpetrator's race, white or black, correctly. The population of potential suspects is 84% white and 16% black. Good. So their race is one of the variables. The race is one of them, and the races are white or black. So that is one of the variables. I'm going to put that here. It doesn't matter if I put it along the column or along the row. Some people really get specific about, the dependent variable goes here and the independent variable goes there. It doesn't really matter though. Our white and our black, and then I need a spot for my total. So I'm going to put that just across the top just because it was the first one that we did. Good, so the suspects and the race, so that was the first one. Then what is the second one? What's the second variable here? Oh yeah, that's exactly it, Bo. So now we're looking to see, did they identify, how was their identification? How did they identify the suspect? Now we do have to be careful about our labels here, because if I identify a white person correctly, then I am identifying them as white. But if I identify a black person correctly, I'm identifying them as black. So in that case, correct means two different things. It means I'm white and black. So instead of using the labels correct and incorrect, that's the right other variable. But instead what I'm going to do is I'm going to label it as identifies them white or identifies them black, because that's how they do it. They're identifying the race as white or black too. So I'm going to put that along this side, is how did they identify them? So they identify the perpetrator as white. And you can see that for this one that will be correct, but for this one that would be an incorrect. Yeah, that's exactly what we're going to be looking for. It's like a true white would be there. And then here, identify as black. And you're right, the true black would be there. And then our total here. So now we're going to fill it in. Now before it was nicely done because it was already gave us numbers in there to begin with. But here, notice I don't have any numbers to begin with. What I have are percentages. So when I start, every time that you're making one of these two-way tables, what you're going to want to start with is your population. That's what you're going to want to start with. You want to start down here with your population. What is my total? So in this case, what are my totals? Like, what are those totals? And it didn't really give me a population. So I can start with any population I want to start with. Because I can start with any one, because it didn't give me any total, I can start with anything I want to. I'm going to start with a nice number to work with. I'm going to start with 100. That's exactly it. I'm going to start with 100. And then what I know is that the population of potential suspects is 84% white. So if I have 100 people, then that tells me that the number of white people I have is 84, because 84% is 84 out of 100. See how easy that was to work with once we have that 100 down there? So choosing 100 to start with is a smart place to begin. And then we know that the rest of them are black. Now, we could leave it like that. We could leave it as 84, 16, and 100. But maybe, instead of using those numbers, maybe we want to make our population 1,000. If I decide to make it 1,000, and I add a 0 there, then all I'm going to do is add a 0 in each one of my columns as well. Because 840 plus 160 equals that 1,000. Sometimes we're going to want to make our numbers bigger to help us to be able to find those percentages easy. So here I use 1,000, maybe even I want to use 10,000. But if I just add a 0 there from the fractions, we see that then it's going to be 1,600 there and 8,400 there. So depending on what size you choose for your population, I always start with 100, and then if I want to add zeros, I add those zeros later. We'll see that again in the next couple of examples. Then from there, I'm going to go back and see what else it tells me. It says the crime scene reenactments show that a particular witness has a 75% chance of identifying perpetrator's race, white or black, correctly. So if I have this many people, and I know that 75% of them I'm going to identify correctly. So I've got 8,400 white people, and 75% of the time I'm going to identify them as white. How many of them did I identify as white? So, I know 75 over 100, or maybe we could have done 3/4. That might have been easier. I'm going to go ahead and just multiply it times this 8,400. Well, my zeros go away, and notice I'm not having to deal with decimals this way. So that I end up with, is that 21 times 3 is 63. So is it 6,300? Y'all check me and make sure I'm right. Divide by 4, which is 21, times 3 is 6,300. This is really just 3/4, right? So that's what I'm doing in my head. I'm saying this is 3/4. 3/4 times that. Well, divide here. Oh, no, it's 21. That's right. Okay. 21, which is 63. Then I know that 75% of the time when they identify someone as black, they actually are black. So I'm going to take again 75% of the 1,600. So again, I'm doing 75% of that 1,600. Or really what I'm going to do is 3/4. I'm going to divide it by 4 to get 4, multiply it by 3 and get 12. So I know this is 1,200. Yay! Then I'm going to do addition and subtraction now to fill in the rest. So I used the information that they gave me, the 84% and 16%. This is like how often they show up in my population. And then my true white and my true black. And now I'm going to just add and subtract to find out the rest. So here, if I subtract that, I get 400 blacks there were identified as white, and 2,100 white people were identified as black, and now I'm going to add across to fill it in. So 6,700 and 3,000 people that direction. Now, if I've done it all correctly, every column and every row should add up. So this should add up to be that 10,000. And we've created there our two-way table. Now, y'all hold on to those notes for tomorrow. Tomorrow we're going to use that two-way table, and we're going to find probabilities using that two-way table. But today's job is just to make the two-way tables. And in your homework tonight, you're going to make two-way tables, and then tomorrow you're going to use them to find probabilities. Okay, let's do the next one. So, where we start, and then we look for to fill in from that population. And we just created our population. We just had to come up with it. On some of the problems, it may tell you out of 200 people or out of 600 people or 1,600 people or whatever. You can use that for your population, but if you need to, you can always add zeros just like we did there. Okay, let's do another. The next one says the prevalence for a certain disease is 1 in 1,600. A test that detects the disease has a sensitivity of 90%. So in other words, 90% of the people who walk in with the disease are going to walk out with a positive test. 90% of the time. When I have the disease, I walk out with that positive test. And a specificity of 95%. So in other words, 95% of the time, when I don't have the disease, I'm going to walk out with a negative test. It's going to tell me 95% of the time that I don't have the disease. All right. And the prevalence is 1 in 1,600. So what are my two variables? That's the first thing I have to start with, or what are the two variables that I'm looking at here in my two-way table? So the first thing is, are they positive for the test? So does the test show them that they are positive, or does the test show that they're negative? So positive and negative positive results or negative results are one of my variables. And then I always have a total down there. Then what's the other one? They either have the disease or they don't have the disease. So that's our other variable. They either have the disease, so in order for them to have a true positive, they have to have the disease and test positive, or they don't have it. And again, we have to have the total there. So those are our variables. They either have the disease or don't have the disease. That's one variable. And then they either get a positive result back or a negative result back. And then there's our total. So where am I going to start? Same spot I'm going to start every single time, which is at the population. Every single time I want to start at this total. That's where I want to begin when I'm creating these two-way tables, is at this total. So when I get ready to do that true positive, they have the disease and their positive is going to go right there. Their true negative, well, they don't have the disease and they're negative here. So when I'm talking about my true positive, that sensitivity, that part's going to be there, and my specificity I'm going to use to find the number here. But you're right, Amani, we're starting at that total. That's where I'm going to start. And in this case, it tells me that the prevalence for the disease is 1 out in 1,600. Maybe we start with that 1,600, since I know it's 1 in 1,600. So my population, or my total this time, I'm going to start with 1,600. Then it says the prevalence is 1 in 1,600. In other words, it shows up in one person out of the 1,600. So I'm going to put that 1 that they have the disease right there in my two-way table, which means now I do perfect, guys, perfect. I'm going to now do my subtraction so that I end up with 1,599 that don't have the disease. Okay, now this 1 here, I don't like to work with it because in a minute I'm going to start taking percentages of it and I'm going to end up with decimals. And just because I don't want to end up with decimals and work with decimals, what I'm going to do is I'm going to add some zeros to this so that I end up with 100 here. Then it'll make it nice and easy to work with. So here, I'm going to put 2 zeros on the end there, add 2 zeros there because I'm just multiplying each part by 100. So if it's 1 out of 1,600, that means it's 100 out of 160,000. So that's how I can make my numbers based upon my population. So it gave me the 1,600, and then I'm just adding 2 zeros to make this number right here a little prettier to work with. Some people like working with decimals though, in which case just leave it as a 1 and you can work with the decimals. But for me, I like to make them bigger to make it easier to work with. Okay, we're always going to start here, total, and then how many out of those population can we find? Like out of the white and black, or here have the disease or don't have the disease. Then I'm going to use my sensitivity and my specificity. So it tells me that the sensitivity is 90%. And I'm going to take 90% of the ones who have the disease, because that 90% is 90% of these guys. So 90 out of 100 end up with a true positive. So that sensitivity I'm using to help me find this number. And I'm taking 90% of these ones that have the disease, which we know 90% of 100 is 90. See how nice and easy, though, that is to find when I'm dealing with 100. Then I subtract, and that means that 10 people who had the disease walked away with a negative test. So I know that's happened to you probably on occasion, where your throat is just killing you, you don't feel well, you go in, you have a test, they tell you it's negative, they send you home and say, wait a few days, you'll be fine. And then after a couple of days, you go back in, you're like, I'm still sick. And they swab you again, and they go, yo, yeah, you do have the disease after all. You're like, yeah, I knew that last time. So maybe you got that negative results. Most of the time, you know, you wait a couple of days and you're in agony, it's all fine. But like when Michael was a baby, we took him in, and they kept sending me away, and it turned out he had meningitis. Well, maybe that's, you know, we want him to catch it a little earlier. But there's that. This is a true positive. These guys are a false negative. They got a negative result, but it was false. It wasn't a true thing. So this is we call that, those 10 people got a false negative. Then we have a specificity of 95%. So I'm going to do 95% of the people who did not have the disease. 95% of the people who do not have the disease got a negative result. So 95, almost everybody who didn't have the disease ended up with a negative result. So 95% of those people without the disease, 159900, walk away without the disease. Well, these zeros go away, those zeros go away, so I'm doing 95 times 1599. That one's not quite as much fun, but at least I'm not dealing with decimals along with it. So I'll do this multiplication. It is 151,905. Okay, so these guys got true negatives. They didn't have the disease, and they walked away with a negative test. That's a true negative. But that means that how many of them walked away with a positive test? How many of these people who didn't have the disease walked away with a positive test? 5 is 9, 9 is 9, that's 7. Is that how many it is? Oops, I'll do it in red since the rest of them are. See if this is right. Subtraction's hard. Oh, good. So this is my specificity. Notice I used my specificity to find out how many people got that true negative. But these people walked away with a false positive. They didn't actually have the disease, even though they walked away with that positive. So you remember at the beginning I told you about my mammogram. And I got this letter in the mail that said you're positive for the disease. The mammogram showing something on your results. So then I'm like wondering, should I worry about this or not worry about this? Should I worry that I got a positive? But I know, because I teach statistics, that there are these things called false positives. You know, I know that there are true positives, but there are also these things called false positives. So when I got my results back, I didn't panic. I didn't freak out because I know about those. So tomorrow we'll learn about the probability that I actually had breast cancer, and then I'll tell you if I did or not. We'll talk about it. So here, now that I have this, we'll add our positive results and we'll add our negative results. And we'll find out those totals. So So that means a total of 5, 18, carry 1, 9, 10, carry 1. 8,885 people walked away with a positive. Even though only 100 of them had the had the disease, 8,085 of them walked away with a positive test result. And then 151,915 people walked away with a negative result. So 159,900 didn't have the disease, and yet we only had 151,915 with negative results. So today our job is just to make the two-way table, and then tomorrow we'll look at the probability that we have the disease or don't have the disease. Let me read it to you. The probability a woman my age has breast cancer is 1%. A mammogram has a sensitivity of 99%. So in other words, 99% of the people who have breast cancer, when they have a mammogram, it's going to catch it. 99% of the time, it catches it. That's a pretty good sensitivity. And then 90% specificity. So in other words, 90% of the time, if you don't have it, it's going to tell you that you don't have the disease. 90% of the time, it's going to tell you you don't have it, that you're fine. All right, so let's build this two-way table. Again, when we're building the two-way table, the first thing we look for are those two variables. So what are the two variables that I'm looking for here? All right, so the first one we have is, do we have the disease or not? So that's the first. And you're right, Bo, that's exactly it. It's going to be the exact same. It's, do we have the disease or we don't have the disease? And our total. And then even this other variable is the same, because we either have a positive test or a negative test. And then our total. There's a total, there's a total, there's a total. Now we're going to fill it in. And where am I going to start? When I get ready to fill this in, where do I start? Good, the population total. So here it says that a woman my age has cancer is 1%. So it doesn't tell me a population in there anywhere. So maybe where I want to start is just 1%. Well, that's 1 out of every 100. So maybe I just want to start with 100. And then from that total, I'm going to look at that prevalence to help me fill in this bottom. So out of my population, how many do I have? Well, I know it's 1 out of 100. So if this one's 1, it makes that one 99. But like we did earlier, I don't want to have to take a decimal. I don't want to have to take a percent of that 1, because then I'm dealing with the decimal. So instead, I'm going to go ahead and ramp up my population to ramp this up. But just a hint, just a clue, it's easier to fill in the table if you'll start with 100. Start with the little numbers so that your subtraction here is easier to do. The minute you start getting bigger, for some reason the subtraction gets harder. So here, 1 and 99 is easy to make 100. But if we do 100, then all of a sudden it gets harder. So now once I have that, I'm going to add 2 zeros there, add 2 zeros there, add 2 zeros there. So 100 out of every 10,000 women have breast cancer, which means there's 9,900 of them that don't. Okay, once we have that, then we're going to start with this sensitivity. And that sensitivity is my true positive. So the ones who have the disease, 99 of them are going to walk away knowing there's something not right. It's going to catch it 99% of the time. That's why they want women to have mammograms. is because most of the time it catches that they have it. So out of 100, 99% of the 100, it says, yes, you have a true positive. You have it and you're positive. But that means that one poor soul walks away without it. One person walks away with their mammogram thinking they're fine, and it turns out that they've got breast cancer. They may end up having other symptoms later or something that let them know, or maybe they go in later for another mammogram and they recognize it then. Then there are 9,900 of them that don't have it, and the specificity is 90%. So 90% of those 9,900 are going to walk away with a negative. They're going to walk away knowing they don't have it. So 90% of 9,900. So again, zeros disappear, and now I'm just doing 90 times 99. Well, that zero on the end is just going to be a 0 here. And now 9 times 9 is 81. Carry my 8. 9 times 9 is 81, 82, 83, 84, 85, 86, 87, 88, 89. So my true positive, have and plus here, sensitivity I use there. My true negative, they don't have it, and they get a negative test, goes here. So my specificity is there. Okay, so 9,900 of them didn't have breast cancer. 8,910 of them walked away going, I don't have breast cancer. So now I'm going to do a little subtraction to find out that 0, 9, 9, I think that's it. 990 end up with walking away with a negative test. Walk away with a positive test. 990 of them start getting anxious. They're worried. Think something's wrong. By the way, when you get a positive test, do you immediately start chopping breasts off? What do you do if you get a positive test? So, okay, so here I'm going to add those together. Did y'all think about that question? And I'm going to add these together. 9, 18, carry 1 is 1,089. That's right. You discuss with your primary care physician about your options. So, and like if you get a strep test, usually they just give you an antibiotic and you go away just taking the antibiotic. But maybe before my doctor started giving me some sort of treatment, there were other tests that I could take to check to make sure I actually had the breast cancer. So before they just start giving me medicine, they do some other tests to check. And we'll talk more about that tomorrow. Notice again that 100 people walked in with breast cancer and 1,089 women walked out thinking they had breast cancer. So, 10 times that amount walked away thinking they had breast cancer. So here is, yeah, I know y'all do. You totally trust your math. Here is our two-way table. So today, your homework, your job is just to create the two-way tables. And then tomorrow, we're going to use those two-way tables to help us find the probability. So what is the probability that me with a positive test actually has the disease? So we're going to look at that tomorrow. I have one more since we have like 1 minute. We'll do one more. You know me, I can't let y'all out on time. That can't happen. So I know y'all can't probably read that one. I'll read it to you. It says, Marie is getting married tomorrow at an outdoor ceremony in the desert. In recent years, it's rained only 5 days each year. When it actually rains, the weatherman correctly forecasts rain 90% of the time. And when it doesn't rain, he incorrectly forecasts rain 10% of the time. So let me put just part of it up here so that you can see the numbers. So 5 days out of the year it rains. He correctly does it 90%, correctly identifies rain 90%, and when it doesn't rain, he says rain 10% of the time. So there's the important information from our thing. I'm going to start with that 365 days. I like it. So I know my total, you're exactly right. My total is going to be the number of days. So you're starting there at that 365, and that is where that's going to be that first number I put in there. Now let's come up with those labels. So what are my labels? You got it exactly, Bo. You got it. That's exactly the thought. So you can even just do it times, 100 here to help you out, or 1,000 there to help you out, as long as you do the other parts as well. Well, we know it's either going to rain or it's not. So one of my labels here is that it rains or there's no rain. Now, this one's the tricky one. Is what is my other one? What is that other label that I'm going to put on here? So this is my tricky one. It's rain and no rain. And this is kind of like the one with the race, where I've got it correctly and incorrectly, but we have to be careful, because if he correctly identifies rain, then he's identifying rain. But if he correctly does no rain, then he's saying no rain. So correct means two different things. So I can't just put correct and incorrect. Instead, I have to put, he says that it's going to rain, or he predicts rain. And here he predicts no rain. And then when he's correct and he says rain, that goes there. But when he's correct and he says no rain, then that goes there. So, we know that 5 days out of the year it rains, which means 360 it does. Maybe we add some zeros just to make it easy for ourselves. Add zeros, add zeros, add zeros, just to make it easy. He correctly predicts rain when it rains 90% of the time. So when it rains, 90% of those days, he's going to say it rains. So out of 500, well, out of 100, it would be 90. So out of 5 of those hundreds, it would be 450, or, 90 out of 100 times 500. So I'm doing 90 times 5, the 0, and then 45, subtract. So 50 days when it rained, he said it didn't rain. Then when it doesn't rain, he says it's going to rain 10% of the time. I feel like his job is easy, that he should just get on every day and just say it's not going to rain. I mean, that might make him, anyway. Okay, so 10% of the time he says he's gonna rain even when it's not. So we know with 10% you just move that decimal over once. So 3,600 of those days he says that it rains when it's not going to. Now I have to subtract. 3,600 minus 3,600. So 0, 0, 4, that had to borrow, so 32. So 32,400 of the days it doesn't rain, and he says it doesn't rain. All right, then we're going to add, so we get 4,050 days he says it does rain. And then here we've got 32,450 where he says no rain. Those should, if I've done it correctly, these should add up to be that 36,500. All right, so your job today is to make the two-way table. And then tomorrow, we'll look at the probability using these two-way tables, using something called Bayes' theorem. It's really just conditional probability, but I'll teach you Bayes' theorem to go along with it. Way to get those pre-assessments done. Good job. We'll talk more about that tomorrow too. And I'll be on Discord if you need me. Math Made Simple at Simpson Math. Thanks for watching.